Greetings. Today we'll be discussing about effect of lack of fit among determinate and indeterminate trusses. Before going towards the analysis of indeterminate trusses, let us try to understand what's the meaning of lack of fit. The trusses are fabricated with a specific amount of tolerance in the length of members so that the member fit perfectly. But there may be errors in the fabrication. The length of member of the truss may be slightly more or less than the required for the perfect assembly. Such a deficiency is termed as a lack of fit. If we talk about the fabrication work of the trusses, first the truss members has been cut down in required length and with the tolerance that they can get fit and assembled at the particular joint. But due to some error, some members may have extra cutting or some member will have undercuts. So these undercuts and extra cutting will raise the problem like a lack of fit. Let's talk about the uh, lack of fit due to short in the length as shown in left hand side figure. It shows that the member is too short, means the member has a length which is less than the required one. What will happen if the deficiency arise in a truss? The fabricator will try to assemble the member at the required position by stretching it, thereby introducing initial tensile stress in the member. Since the member is connected on either end with reference to with other members in the geometry, the other members in the geometry will be subjected to compression to get adjusted in the given geometry. Thereby, the truss is subjected to additional stresses prior to the application of the external load. Similar the case will happen if we look towards the right hand side. In case of a member which is too long, means the length of the member is slightly larger, lack of fit is due to larger in length. The fabricator will try to adjust it by compressing the member or compressing the member to fit in the position. Thereby, the compressive stresses will be developed and the other end members which are connected with this member will subjected to a tensile force, and thereby the entire structure will be subjected to additional stresses prior to the application of the loading. So if we talk about analysis and effect of this lack of fit in the member, let's try to get this understanding with reference to the member forces, estimation of the member forces in determinate and indeterminate trusses with numerical examples. The numerical number 14, which has a statement for the truss shown in below, the member PQ is the short by 3 mm. What is the magnitude of vertical displacement of joint R in mm? So given assembly, there is a member PQ is being short in length by 3 mm, and he says that what will be the uh, displacement observed at R due to this deficiency, lack of fit. So if we talk about the adjustment of this, when we try to adjust this one PQ to be moved at the joint Q, the joint Q is having a roller support. It will have the translation deformation here. It will move slightly inside, and thereby there will be the displacement in member PR and RQ. This displacement will be traced with reference to the position of R, joint R, whether it will move upward or downward, and thereby it will try to adjust the geometry. If we talk about the geometry here, the geometry is said to be a perfect truss because the unknown members count and the member forces count are nearly equal. That's why it is statically admissible. But since there is no external loading, we can say RP is equals to RQ in magnitude but opposite in direction, and the horizontal reactive force will have negligible effect since there is no external loads applied in horizontal direction. Where we are interested to know in the displacement at the joint R. So we'll utilize here Castigliano first theorem, which states that if we take partial derivative of the strain energy stored by the system with reference to the force which is responsible to cause the displacement at the particular location, means you can get di by equals to dou u upon dou r. If I say r at r, I am going to apply here a force here. So I will use concept of unit load. So what I will do, I will apply unit load and I'll try to get the effect of this unit load among the other members. So we can write the equation of Castigliano first theorem in a rearranged format like summation of Pi Ki Li divided by Ai into E. It is the original equation which we have derived with reference to the Castigliano theorem. If I take the components like Pi, Li upon Ai into E on one side and Ki as a component part in multiplication, then we can say this component part which are assembled together represents the deformation in individual member. If I try to assemble deformation of all the members of a trusses and multiply by the unit load effect here, unit load coefficient here, I am going to get the displacement of the entire truss. So we can write here summation of delta I into Ki. Now I will utilize this equation to find out the total displacement of the system. Now if I move towards the estimation of the coefficient of forces, since there is no external load, so what we will do, we will apply unit load at the joint R of unit load and try to get the coefficients of this distribution of unit load among the other members. For that we have to go with joint by joint analysis. So under the application of unit load, the reactive forces at the P and Q will be equals to 0.5. Since the geometry is a symmetric one, we can say the Rp equals to Rq, which equals to 1 by 2, that's W by 2, it comes to 0.5 kilonewton. Now we'll try to analyze the member forces by joint method. So let's go with a joint P first. At joint P we see that there are 4 forces acting at joint P. The member force K1, the member force K3 and the reactive force Rp, which have a magnitude 0.5 kilonewton, and HP has a negligible effect, that's why I have considered it as a 0 member force. Now if I talk about the equilibrium of the vectors here, so 0.5 kilonewton, the reactive force is going upward. So I am going to consider the member force Rp, which is represented as a K1 going downwards, so that vertical component of the K1 force will be in equilibrium with the vector of the reactive force, and similarly the horizontal component of the K1 is going towards left hand side, so I am going to consider K3 going to the right hand side. So likewise one may have the equilibrium and sign convention here, or vice versa. There is flexibility for the analyzer how he want to consider the direction. Now we'll talk about the positioning of the inclined member with reference to horizontal axis. From the geometry we can say theta is equals to tan inverse 4 by 1.5 the vertical by the horizontal intercept, resulting into a value 63.43. In analysis we require sine and cos component, that's why I will immediately count the cos and sine components of that. It comes to 0.447 in terms of cos and 0.894 in terms of sine. Now we'll apply static equilibrium equation for this free body diagram. So what the resultant, I will get summation of Fi equals to 0, resulting into value minus K1 sine of theta, the vertical component going downwards, plus 0.5 equals to 0, resulting into a value of K1 as 0.6 kilonewton compressive in nature. Similarly, if I apply a static equilibrium equation in horizontal axis, then I will getting minus K1 cos theta plus K3 equals to 0, resulting into value of K3 equals to 0.268 kilonewton tensile in nature. Now I will utilize the symmetry of the section and can say that K1 is equals to K2, which equals to 0.60 kilonewton. There is symmetry in loads as well as symmetry in the geometry, that's why we can state this one K1 equals to K2, which equals to 0.60 kilonewton. Now we'll try to find out what is the displacement observed at the joint R due to application of unit load at R. For that we'll put the results into tabular format. Very first column will be members PR, RQ and PQ. Then I am taking a product PL upon A, which is said to be individual deformation of the member. Since PR is there is no deficiency observed, that's why I am putting here 0. Similarly RQ no deficiency is there 0, and PQ it is short in length, means it has a lesser in length, that's why I am going to put here what amount of the shortage it has, that is nothing but deformation, initial deformation given to us, that is minus 3, which is in mm, minus 3 mm given to us. Now K coefficient I will put in assembly. For PR we got 0.6, for RQ we get 0.6. They are positive in nature since the forces were compressive in nature, and PQ we have considered the force is tensile in nature, minus 0.268 kilonewton was the magnitude of that tensile force. Now we require the product PKL upon A, since the first two element has a zero contribution here, that's why it will be 0, and the second product result into a value 0.804, which says that there will be displacement of the joint of amount 0.804 mm in downward direction. Means what, we can make a statement here when the statically admissible structure is subjected to lack of fit, there will be no stresses develop in the member. Okay, only there will be adjustment of the deformation among the members. Okay, with this I will end today's lecture. We'll meet in next lecture with analysis of indeterminate structure under the action of lack of fit. Till then, stay at home, be safe, be healthy. Thank you.